All right, so today I'm hoping to finish the lecture on numerical differentiation. And if we have time, come back. Welcome back, Emily. And hopefully everything is okay. So we're, that's what matters. That's same for us. That's like, they have, yep. Thankfully, they're quite resilient. Yeah. Okay, so today I would like to finish numerical differentiation. And if we have time by the end of the lecture, I will go over the regression homework assignment because we will unlikely be able to return the graded version of the homework to you. So I'll discuss it briefly if we still have time. So it's in our best interest to try to push through the numerical differentiation. Again, the numerical differentiation was a precursor topic for ordinary differential equations and partial differential equations that we're going to talk about. Last time we left off talking about the order of accuracy of a method, and we introduced the notation, this scripted O or the big O notation. A method is said to be order h to the power p, where h is the spacing in a finite difference method. So that's how far the points are spread apart. P is called the order of accuracy. A method is said to be order of order h to the power p if the truncation error has the form constant times h to the power p. And that truncation error essentially is represented by the leading order term in that error. The first term in that error typically dominates the entire error, so the entire error behaves. That's what the big O notation says, is that that entire error behaves as if it's a constant times h to the power p. Now, to calculate p, you got to do some acrobatics in your code, but there's a faster way to get an idea of what p is, and is that if you are able to compute this error, which you are in many cases by just doing a higher order approximation versus a lower order approximation, so a method of order 3 versus a method of order 1, for example, then you can estimate that error. Then if you plot the error on a log-log plot, so if you take the logarithm of e and the logarithm of ch to the p, what you get is log e equal log c plus p log h. And then if you plot log e versus log h, then that becomes a straight line, and the slope of that straight line is p. Okay? So here's the situation. You have a method, you're trying it out. You expect it to be, say, order 3. You compute the error. How do you estimate the order? You just plot the error versus the spacing, okay? And look at the slope of that straight line. If that slope is 3, then your method is indeed behaving as you intended it to behave. If it's any other slope, then something is wrong. Okay? These are called convergence plots. They are so abundant and predominant in any type of computational method for differential equations. Okay? Like if you look at our research papers, every paper we have, at nearly 99% of those papers, they contain order of accuracy plots. Okay? So we're going to do an exercise together. And we're going to do an exercise together about this. So far, we're working with this forward difference approximation, where f prime of I is approximated as f prime at I plus 1 minus f at I plus 1 minus f at I over the spacing h. Okay, so we're going to test this method. We said that this method is order h, so it's first order. So if we plot the error versus the spacing, so as you change the spacing, you compute the error. If we plot the error versus the spacing on a log-log plot, we should expect a straight line, okay, with a slope of 1 exactly. Okay, so we're going to try out this approximation and verify that it's indeed order h, okay, for f of x equal e to the exponential x. We did this exercise in the first homework assignment, okay, where we tested this forward difference. So we're going to do it again now, but we have a better understanding of what's going on. So for the exponential function, plot the absolute true error for f prime of 2. So why we can do the true error here? Because we know the true derivative of the exponential, which is the exponential, and we know the true value of f prime of 2, which is e to the exponential 2. And then we want to compare that to using the forward difference formula, okay? And we're going to plot, we're going to calculate the error for different values of h, ranging from 10 to the minus 5 to 1. So we're going to do this approximation for h equal 10 to the minus 5, 10 to the minus 4, etc., all the way to 1. And then we're going to plot the error on a log-log plot. So get your Jupyter notebooks up and running. This exercise is strictly to illustrate this idea of the convergence of the error on a log-log plot, okay? So let's get a Jupyter notebook up and running. No, we talked about that last time. Integration and differentiation is not on the exam. Only interpolation and regression. I hope to at least give you one homework on a piece of material before kind of putting it on the exam, okay? So, all right. So let's see. We're going to import our boilerplate. You can just copy those from any other notebook. Or some of you have this kind of master notebook. Just have everything imported. So NumPy, you don't have to do the matplotlib magic, but I like to do it for better quality plots. And then you need at least NumPy and matplotlib, okay? So for the function, for f of x, let me do some LaTeX, f of x equal e to the x, okay? Compute the absolute true error for f prime of 2 using the forward difference formula, okay? And plot the results on a log-log plot. Use values of h ranging from 1 e to the minus 5 to 1. Okay? Okay, so first we're going to compute the true value. True value is equal mp.exponential 2. So this is the true value. This is the true value of f prime of 2. Agreed? Because the derivative of f of e to the x is e to the x. So evaluated at 2, just e to the power 2. Okay. Now define a forward difference routine. So I'm going to call this df dx, okay, or df. Okay. And what does that routine need for a continuous functions rather than a discrete set of data? For a continuous function, it needs a function name, okay, which is another Python routine. In this case, this will be the exponential, right? So we're going to pass this as an argument, f, which is the function we want to differentiate, the point at which we want to find that derivative, approximation, and the spacing, h. Okay. Now we will interchangeably use h and delta x. Okay, so don't be confused with that mix in notation. Okay, they are both used. Okay, h and delta x, they mean the spacing. Okay. All right, and we're going to return. So that is going to approximate the derivative at x at the value at the point x, and it's going to be f at x plus h minus f at x over h. Okay? Perfect. So now you can call this and say, you know, apply this at point 2 with the spacing 0.1 is just going to give you a value. Okay? If you print the true value here, just to get you an idea of what this is, right? So clearly, as we reduce the spacing, that value is going to become more and more accurate. But now my objective is to see how this value changes, or how the error in this value changes as we refine, as we get smaller and smaller h values. So we're going to create a lin space for h, np dot. You guys in the back seeing okay? Okay. So we could create those h values manually by hand. So you could do an numpy array and do 1e to the minus 5, 1e to the minus 4, etc., right? Or you can just create a lin space, which is easier. np dot lin space, going from 1e to the minus 5 to 1. Okay, and it's going to default to 50 values. Okay, so those are the values of h. xi is 2. Okay, and then numerical derivatives numeric derivatives, say, is simply applying df, the exponential at point xi, and with all those spacings h. Okay. So what does numeric derivatives contain? Contains all the numerical derivatives evaluated at all of those different values of h. Okay? Clearly, as we approach spacing of 1, we are way, way far away from the true value. At spacing 10 to the minus 5, we're pretty close, 7.389, and then for the next value, 7.46, and so on. Okay? So this array contains the forward difference approximation of the exponential, of the derivative of the exponential at 0.2, but for different values of h. What are those values of h? They're the values in the lin space, okay? So if you print h, okay, 10 to the minus 5, to 10 to the minus 2, etc., and so on, okay? Those are all the values in that lin space. Okay. So now to compute the error, I need the true values, right? So all I have to do is say true error is the absolute value of the numerical derivatives minus the true value. Agreed? That's the true error. All of those derivatives, I'm subtracting from them the true value, taking the absolute value. I'm not doing any relative error, nothing, because here I'm trying to get that convergence plot. And that convergence plot does not need a relative error. I'm interested here in finding that convergence rate, and indeed to prove that the order of accuracy is 1. Okay, so now we can print the error versus h. So if you go and do plt.log, and on the x-axis you put h, and on the y-axis you put true error. Okay, I'm going to do a black line. You get a straight line. Okay. Now I can tell this has slope of 1. But if you're not sure of that, it has a slope of 1. You can plot a function that actually has a slope of 1. So if you plot h versus h on a log-log plot, that's going to be a straight line with a slope of 1, right? So we compare it, plt.log h versus h simply, do a dash dot. You see they're parallel to each other. Because this blue line, we know for sure it's h versus h, right? So the log of h has just slope 1, right? The coefficient of log h has slope 1, okay? Is 1. So it cuts it right in the middle, okay? And so given that they're parallel, they have the same slope. This one has slope 1, so therefore this one has slope 1. What does that tell us about the method? That the method is first order. Yes?
It's probably just because of like ground off or something, but the black line is not straight. Oh, and
Well, no, the black line. So as you go to higher value, that's a good observation, Brent. As you go to higher values of h, we hit something called non-asymptotic regime. So you shouldn't worry about that. What matters is that we have some range where that slope is actually 1. And if we continue decreasing h, as we showed in one of the examples in the past, that error is going to start going up where round-off error actually dominates over there, okay? So what matters is that there is a range where that slope is actually equal to 1. Even 2 points are enough to show that the convergence rate is 1, okay? But that's a good observation. But over here, it's all straight. Look at that, okay? Okay, we'll try later with a method that is second order, and we'll see how it converges at a higher order. But first, let's get back to the slides. Okay. Okay. So now, remember we were starting with discrete data. We took this kind of side tangent to look at this order of accuracy, etc. Now we're going to get back to practice. And we were dealing with discrete data, okay? And this forward approximation, if you have discrete data like this, you can evaluate the derivatives at every point using the value at I and the value at I plus 1. So you can evaluate the derivative at point I using the values at I and the value at I plus 1, okay? Now what happens at that last point over there? How can you, can you use this formula to evaluate the derivative at that last point? Can you use this formula to evaluate the derivative at that last point? No. Yeah. So you're correct. Yeah. Why? Yeah, we don't have an extra point. So the derivative at point n, according to this approximation, is fn plus 1 minus fn over h. But there's no fn plus 1. Doesn't exist. It's not in the data. So what do you do in that case?
What if we use n minus 1?
Okay, so we need to develop another formula that is, rather than using a forward difference, maybe you can have a formula that uses a backward difference, right? And indeed, that's exactly what we will do. Okay? So in this case, we need to derive this other formula that uses the interior points only. And so we write the Taylor series. It all goes back to this Taylor series. Remember, in the forward difference approximation, we did the Taylor series at I plus 1 in terms of I. Now we need to do the Taylor series at I minus 1 in terms of I, so that we can extract the derivative f prime at I in terms of I minus 1. Okay? So you do the same thing. You repeat the same strategy. This is, we change the symbols over here. So fi minus 1 is fi minus h f prime I, etc. If you eliminate all the high order terms and extract f prime I, put it on the left, you get fi minus 1 over h plus order h. It's a first order method. So this backward difference formula, this is what it's called, the backward difference formula. It's a first order method, so similar to the forward difference, but you can use it at that last data point. Okay? So you can apply the forward difference everywhere until you hit that last data point, and then you apply the backward difference. Or you can apply the backward difference everywhere until you hit the first point where you apply the forward difference. Both methods have the same order of accuracy, so there will not be a significant difference. Okay? Now, visually, the backward difference formula, if this is the true slope, the backward difference formula uses the point to the left of point I and gives you this approximation to the slope, okay? As compared to the forward difference, where it was using fi plus 1 and fi, so the slope was completely opposite to that one, okay? All right, so now we can keep building methods using these Taylor series. We can combine Taylor series at fi plus 1, fi minus 1, fi plus 2, fi minus 2. We can combine them in all sorts of ways to develop methods that have even higher order. So let's say you want to evaluate the derivative, but you want your error to be even smaller for that same spacing. The only way to do this is to have a higher order method. That p exponent in order h to the p, the higher it is, the more accurate the method it is. So the question is, can we develop methods of order h squared, for example? Absolutely. All right, here's an example of how we can do that. If we take fi plus 1, this is the Taylor series, and fi minus 1, this is the Taylor series. Note the negative sign here, okay, minus h, okay, minus h cubed here, okay. Then I have an activity here. Combine these two formulas to develop a second order approximation for the first derivative. Your goal is to eliminate the second order term, h squared f double prime. So what would you do to these two values, okay, to these two Taylor series? How would you maybe add them together and see if you can extract f prime, so that you eliminate this term, okay? You have f prime, maybe subtract them from each other, and then you would have only the h cubed term. Okay, so subtract. So mine is saying subtract and divide by 2. Okay, right. Okay, so let's go ahead and subtract them. What you get is fi plus 1 minus fi minus 1 equal 0 for fi because it's fi minus fi, right? And then for hf prime, we want the expression to have f prime because we're after f prime, right? So you have 2h f prime at I. Now what happens to the h cubed term? It goes to 0. That's sorry, for the h squared term, it goes to 0. That's what's so great about this. And then you have the h cubed term. Now what happens when you take f prime to the left-hand side? You're going to divide by h, right? And that makes h cubed h squared, and then you have an h squared method. So if you, from this expression, if you extract f prime I, you have what's called the central difference formula, which is fi plus 1 minus fi minus 1 over 2h plus order h squared. So if we go back to our notebook now and use this formula, the line we plot is going to have a slope of 2. Okay, so let's go ahead and try that. So I'm going to define another one here and say df2 fxh. I'm going to return f at x plus h minus f at x minus h over 2h. Okay? We claim that this method is second order. Okay? So again, numeric derivatives 2 is equal xi and h. So now I'm computing numerical derivatives using this central formula, okay? And I'm going to compute the error in this central formula, right? Numeric derivatives 2, okay? Then true error 2 for central, essentially, is also the absolute value of the numeric derivatives 2 minus the true value. Okay, let's see if it works. True error 2. Okay, look at that. So now, this red line corresponds to the error, to how the error changes as we change h for the central approximation. And it has a slope of 2. To verify that, you also plot a curve that has a slope of 2. So you can plot h and h squared, for example. And then you see that they're almost parallel, okay, over here. They diverge a little bit over here as we get to smaller and smaller h, but that's fine. What matters is that we captured a range where that error changes correctly as a second order, with a slope of 2, okay? Now, if you were to go to the actual array of the errors and compute the slope of that line, you can take the difference between the logs of two consecutive errors and try to evaluate the slope from that. You can do that. Just requires a little bit more acrobatics to get this done. Okay?
So the numerical derivative 2, I think you showed us this formula before. Was the thing on the previous slide just the derivation for that?
Pardon me?
I think you showed us this formula before. Was the thing on the previous slide just the derivation for that?
Yeah. Yeah, we saw this in the past. Right now, we have a little bit of formalism on what we mean by this order of accuracy. So now the central approximation, because it's a higher order method, it's closer to the true slope. The error is always smaller in this higher order method. Okay? These are three standard methods for evaluating derivatives of functions or of discrete data. And you can use all three in your homework. You're going to have a bunch of discrete data, and you're going to use all of those formulas to approximate the derivatives and the slopes of those data. Okay? Pardon me? The central one is the most accurate. Okay. So what you could do then is, when you can use a central difference formula, you should use it. Or a higher order formula without incurring significant cost, you should use it. Yes?
So would we say that the central difference formula has an order of convergence of 2?
Yeah. It means that if you cut h, like we said, if you cut h in half, okay, you're going to cut the error by a factor of 4. Whereas for the first, yes, that's exactly the same. Or you can say it's a second order method or order of convergence of 2. They're both the same thing, mean the same thing. So then with discrete data, then you could say, well, Professor Saad, let's use a second order approximation everywhere we can. But where we cannot, maybe perhaps use the forward difference on the left-hand side and the backward difference on the right side of these data points, right? Okay. That's reasonable. Okay. So here, this is what we're going to do. We're going to develop a Python code to find the first derivative of the discrete data in general, and then apply it to analyze the COVID-19 data that we started with. If you remember that lecture last Thursday, we had a bunch of COVID data, and we wanted to estimate the infection rate. Okay, so we have a bunch of discrete data like those points, and we're going to use a central difference everywhere in the middle. We're going to use a forward difference on the left and a backward difference on the right. Why? Because we cannot use the central difference on those points at the endpoints, right? Because you need either the point to the left of the data, to the right of the data, which don't exist. So you have to defer to a one-sided approximation. Okay, so let's do this in Python. Let's see. Did we have a notebook for those COVID data? Or not? Did we do it? Yeah, COVID-19 China total daily cases and COVID-19 world total daily cases. There is a notebook in Canvas. You can use that, but it has gaps in it. But if you want to just work with me, just download those two data files from the numerical differentiation, from the differentiation module. There's two data files. So let's see. yi China is equal mp.load txt of COVID-19. Yep. So there's the COVID-19 China total daily cases.txt. Okay. And then the yi world. Were you able to find those files on Canvas? Just download them, put them next to your notebook. COVID-19 total daily cases for the world. Okay. So now I don't have X data for those points, but I don't need X data because these are daily cases. So I'll just start counting from day 0, okay? So all we need for the x data is to generate a length space, or just a range from 0 to the number of data points, okay? So n is, let's say, len yi China, okay? And then the xi data is numpy.arange from 0 to n, okay? Because I want to plot those data. T.plot, xi, yi China, and we're going to do squares, C, okay? And then plt.plot, xi, yi world. And I'm also going to do disks, okay? Now, don't make, in your homework assignments, in your reports, in any of your future work and courses, put legends on your plots, put labels on your axes. I don't do this in class because I will, every extra minute I spend, it's one less minute I go over lecture material, etc. So it's not, don't take that habit from me, but please add labels and legends to your plots. A plot should stand on its own merit. If someone looks at it out of context, they'll be able to tell, oh yeah, this is total cases of COVID versus, days, and this is for China and the world, right? If you show them a plot like this, there's no idea what's going on. I don't put legends and labels here because it will, for all the plots that I do in the class, be a huge waste of time, okay? But it's not a waste of time in your reports and like the formal work you're doing, okay? So please don't take this habit from me, okay? Like in my notebooks here that I use formally, okay, this is what I have over here. Okay, it's like I have every single detail, okay, yi world. Okay, so I have clear details, okay? Yes?
That np.range command, why do we use that instead of linspace?
Linspace is because I need an integer day, 0, 1, 2. With linspace, you're going to have not necessarily a non-integer result, right?
Okay.
Yeah. So I use the arange in this case. All right. So now we're going to differentiate. We're going to create a general subroutine, which you can use in your homework. You're welcome. To evaluate the derivatives of discrete data. Okay. df discrete. So evaluates the first derivative of discrete data. For discrete data, I need values of xi and fi values, okay? So general subroutine for computing first derivative of discrete data, okay? Data assumes equal spacing. Now, when we use the second, when we use the central approximation, we assume that all the data points are equally spaced. That fi plus 1 is h distance away from fi, and fi minus 1 is also h distance away, so that we were able to combine them. If you did not have equal spacing, this will not work, okay? All right, so we're going to do, first, for our spacing, or h, let's call it h, it's xi. If it's equal spacing, then you can take the difference between any 2 points. You're going to take between the first point and the first 2 points, okay? First and second point, and then result, I'm going to store all of those derivatives in a NumPy array. I'm going to make it like fi, okay? So same size of fi. Now, for the first point, result 0, and we're going to do a forward difference approximation. And that's fi at 1 minus fi at 0, okay, over h. Forward difference at the leftmost point. Okay, and then in the middle, or at the other side, sorry, the last point is fi minus 1 minus fi at minus 2, right? The circular indexing over h. So backward difference at the rightmost point, right? And then in the middle, result, if you remember the splicing, so going from 1, so I equal 1 to n minus 1, those points, we can evaluate the derivatives there using a central differencing scheme. And we're going to do f at I plus 1. Okay, so fi are the values of the data. So we're going to go I plus 1 minus fi I minus 1, okay, over 2h.
What does the column in the brackets do?
It splices the array. Okay, we've used that plenty of times, right? It takes a subset of the array. So the bracket, you access the array, right? The bracket is to access the array. This gives access to a range in the array. So we're only accessing the first point to the point before last. Okay, because the first point, not the first point, the second point to the point before last. The first point we applied forward difference. The last point we applied backward difference. Okay. I want all the way to n minus 1 essentially. And then same thing here. This goes fi plus 1, so from point 2, 3 all the way to the end. And this one goes from point 0, 1 all the way to the second from last point. So that gives you two arrays, the arrays of fi plus 1 and the arrays of fi minus 1. We can do that whole thing in one shot. We did this before a few times. So I don't know. So return result. Okay. To importing the data. Yeah. So mp.load.txt. This is a simple way to load just numerical data from a text file. I know many of you are using pandas and etc. It's way overcomplicated for most of the things you need. All right. Okay, so now we can use this routine to compute the rates of change for, let's say, rates China, for China, df dx, using the China data. Okay, and then rates world equal df dx xi yi world. Okay, and let's, oops, it's not df discrete, sorry. df discrete, my bad. T.plot. So we're going to plot now xi rates China. We're going to do those as squares. And then rates world. We're going to do those as circles. And you can see the rate of change of infections. Okay, there's like some spike going on over here. I would call this an outlier. But they're both steadily rising because before, in the first 30 days of the pandemic, if you remember, it was all concentrated in Wuhan and the region around it. But then, as people started developing immunity, etc., and the lockdowns in China, the rates started going down in China, but then the world infections started spreading across the world, so the rates kept going higher and higher. Okay, these are true values, like 2,000 infections per day, right? Because the x-axis is day. Okay. Doing it with discrete data. Okay. So we'll do a similar exercise, although by hand. I think most of it's going to be by hand, the homework. Yes?
Can we go back up? I want to see
For xi? Yeah. So for xi, yeah, I just created a range because typically you're given x and y data. But in this case, where we're not given x data, it was just per day, every day. So I just created my own array, counting from day 0 to day whatever, however many days were collected. Okay? Yes?
So a range pretty much doesn't have space button.
No, well, no. It just gives you, no, not complicated. It's just, it serves a different purpose. It's just a counter. Just like range for I in range, numpy.arange gives you a numpy array with integers in it going from start to end minus 1. That's it. If you call range, range doesn't, the standard Python range when we do for I in range 0 to n, range is not an array. Range is a function that is called regularly. If you want an array of integers from start to stop, okay, you have to call a range, okay? Yeah, yeah. And if you're in doubt, just print it. So, you know, an numpy.arange from, you know, 0 to 10 is just going to give you a numpy array. If you do range from 0 to 10, it's just going to give you range from 0 to 10. It's not an array. This range function, the standard Python function, it's used strictly for loops. It's an automatic counter. It doesn't give you an array. Arange gives you an array with integers, okay? All right. So let's proceed. There's still a few things. Someone can tell me where my cursor is. Okay, there he is. Okay. So now, list one problem with this approach. There are a couple of problems. Just want you to list one of them. Miles.
What if the data are different sizes? Like one
Yeah.
is 1,000 days, one is 1,002 days.
Yeah. Yeah. So if the data are not equally spaced, is that what you mean? Yeah. So if the data are not equally spaced, we cannot use the central difference approximation. In the middle, you'd have to use forward or backward or develop your own central difference with unequally spaced points. Okay. What's another problem?
I was just going to ask, there's not like any Python routine or like numerical you can use.
This is better. There are some built in Python, but I don't recommend those. Okay. Building your own is better. Okay, because you have no control what it's going to do at the endpoints. Okay, we have to. So I don't know who raised their hand first, Connor.
Well, the point after f prime of x, you're using for the first derivative of the first point and the middle point, so you're biasing that data point, like it's coming more than once.
That's not going to be necessarily an issue, at least for just computing derivatives. This might be an issue when you're doing something called advection. If the flow is going in the from left to right and you're biasing it from right to left, then you don't have information coming from right to left. Actually, your calculation will become unstable. Okay, but that's more for when we apply this to ODEs or PDEs. Okay. Truncation error. So they both have truncation errors, but let's build on that. So all of these methods have truncation errors. But what about the truncation error for each one of them? So the forward difference, what's the truncation error? Order? What about the backward difference? It doesn't matter. 2h, 3h, still order h, right? What about the central? H squared. Right? So in the middle, you have a second order method. And at the endpoints, you have a first order method. And a chain is as strong as its weakest link. So your overall accuracy in the problem is going to be polluted by the first order error introduced at the endpoints. This will become apparent when we have boundary value problems. Because the boundary value, if you do a low order approximation at the endpoints and a higher order in the middle, the higher order is not going to matter anymore in the middle because that first order error is going to propagate. And as it propagates, it dominates the second order method because the h squared term is going to be pushed away by the h term, by the order h. Okay? So that's a problem with this method. Now you could say, could we develop one-sided approximations at the endpoints that are order h squared? Absolutely. Okay? And we will see this next. Okay? So this is a table of some approximations that you could use. On the first column, you have the formula, and here I'm using delta x instead of h. Okay? On the second column, you have the order of accuracy, so you have order h, second order methods, and you have the type of differencing forward or backward. This is the only central differencing one we have, and this is the requirement whether you need constant spacing. Okay, so the advantage of the first order forward and backward difference formulas is that you don't require constant spacing. But if you need higher order so that you can use central in the middle, higher order forward and backward, then you need to get to these formulas. Look at this formula, for example. This is a second order forward difference approximation. It uses point I plus 1 and point I plus 2. So if you're at the left end of the data, you use the point I plus 1, point I plus 2, okay? And you get a second order approximation. If you are at the other point of the data, you use fi minus 1, and fi minus 2. Okay? So it's a higher order backward difference, and it's second order. So then you can use second order everywhere, which makes your method consistent, and you're not going to pollute your data with lower order errors. Okay? You can do the same thing with second derivatives. And the objective would be now to find approximations for f double prime of I using fi plus 1, fi minus 1, fi plus 2, fi minus 2, whatever is available. Okay? And the idea is the same. You write a Taylor series for fi plus 1, fi minus 1, fi plus 2, fi minus 2, and you combine them linearly, okay, to find those coefficients. So here's an example for a second order, for a second derivative. If you write fi plus 1 and fi minus 1 Taylor series, right? Just write them however many terms you want. We'll truncate as needed. And if you add those two, you get fi plus 1 plus fi minus 1. Over here, you get 2fi. Then the first derivative cancels out, which is great, right? So we don't have to worry about combining it in a way to cancel the first derivative. Then you have the second derivative, which we're after. And then this one goes to 0. And then you have a fourth derivative here, so which is interesting, because now you got rid of the h cubed term. Then you move h squared f double prime to the left. This is what you get. You divide by h squared, and you get an approximation for the second derivative. Fi plus 1 minus 2fi plus fi minus 1 over h squared minus something. This is going to be our truncation error. Okay? And it's going to be order h squared. So by default, the second derivative, by definition, their errors are order h squared. The lowest error you can get with the second derivative approximation. Now, if you remember the heat transfer problem, I told you when we had the d2t by dx squared, and we converted that to ti plus 1 minus 2ti plus ti minus 1. This is where this is coming from. Okay. Way long ago for linear solvers, right? So we're going to revisit that problem and actually derive that system now. Okay? But this is where it's coming from. There's just no mystery. Just approximating that derivative, because now I have values at discrete points, okay, rather than a continuous derivative. Okay? And you can do all sorts of things with this approach. For example, you can build actually a first order second derivative that is one-sided. I need to double check that order. That is one-sided, okay, using fi plus 1 and fi plus 2. So let's say you are facing the same problem, computing that first derivative, but now you need a second derivative at the endpoints. What do? You need to one-side it, okay? Now, when you see a formula like this, okay, what do you do when if I ask you in a bonus problem, let's say, show that, I put like 5 terms up there. What do? You just write the Taylor series for those, okay? So write the Taylor series of fi plus 1 and fi plus 2, and then combine them and see how all the terms eliminate with each other. So let's just do this together. Fi is Fi. So remember that formula. Where was it? Was Fi minus 2Fi plus 1 plus Fi plus 2 over h squared. That was an approximation, a forward approximation for the second derivative. So Fi is Fi. Minus 2Fi plus 1 is the Taylor series of Fi plus 1 multiplied by minus 2. And this is the Taylor series for Fi plus 2. Notice at Fi plus 2, you get 2h, and then 4h squared, and 8h cubed, etc. Now, if you combine them according to that formula, you're going to get h squared f double prime equal that guy, right? And then you divide by h squared, you get that approximation indeed. And the order of accuracy is going to be order h. So when you see a formula, there's a typo here. Let me fix it. When you see a formula like this on your homework or your exam, just write the Taylor series for the different terms. So if you give you a formula like this and tell you verify that indeed this formula is an approximation to f double prime with such an order of accuracy, you just do Taylor series of this, Taylor series of that, and you combine them this way, excuse me, and you verify this, okay? That's as far as I will ask you for this, for building finite difference formulas. Again, this is a table for the second derivative, okay, using forward or backward differencing, okay? In all of those cases, the spacing needs to be constant, okay? Otherwise, none of these formulas will work. Ethan? Yeah, no, that was not right, okay? Yeah. So you can do a forward and backward difference. That is first order, okay? Central is second order, but then you can build forward and backward with second order, but look at how many points you need to use. I plus 1, I plus 2, I plus 3. So you need to reach into, pull more data to build a higher approximation for the derivative, okay? So if you're given data, all you need to do is just apply these formulas. So in the homework, you're going to do first and second derivative, okay, for a flying saucer in Salt Lake City. And you want to calculate the speed and how fast it's moving and its acceleration. So you'll be a flying saucer, a UFO. Yeah. Yeah. You've never heard of that word?
I've heard of it.
So archaic. Yes, thank you, Miles. I call it wisdom. And I'm working on my vocabulary because you guys asked I have better function definitions, okay? So this will be it for finite differences.